Okay, we're going to do the last question of the test, and it's the first part of this is actually quite straightforward. If you've been successful at getting the first part done and got your feasible region and your points of intersection, those aren't being touched. So your feasible region and your points of intersection are basically staying the same, and they're here. And you've got your points, 4 points of intersection within that feasible region. And the ones that you used previous question, you use for here. The thing that's changed is your profit equation, and it is now 49x plus 28y. And so the obvious thing to do is to take those points from your feasible region and stick them in to that now, and to see what your maximum profit is. And we've done that, but you'll notice that that table that you're looking at, there's something very special about the table. First of all, they've used the original points, 9.333 and 18.666, which we can't actually use in the context when we actually answer the question, because we can't have 9.33 single or double bids. But that we still put it in the table to look at what we're going to get for a maximum profit. And so you'll notice that the significant thing is that we have two different combinations, 4 and 28, and the 9.3333 and the 18.66666, which both give me the same maximum profit. So here's where the question becomes an excellence question, because you have to explain why that is happening. So to explain why that is happening, it takes some understanding of sliding lines and gradients, and this is what we talked about in class. Now, the first thing that you need to do is take a look at how this profit equation line is going to be different from the original. All right? So you want to look at finding the gradient of this. Now you say you can't find the gradient of it, but you can. You just have to, in equals k, some profit, doesn't matter what it is, and you rearrange this thing, you get 28y is equal to negative 49, and you divide by 28, and you'll end up getting this profit equation, this optimum solution, to have a gradient of negative 1.75. All right? Now, what I've done is I've drawn two lines that you'll notice here, and these are the old and the new optimum solution equations. One that we did from the question before, and the one that the new one, the 49.28y. So let's just take a look physically at what we're looking at here. Okay, so what we're looking at, this black line represents the old gradient function, and if we pass that through the feasible region, we can see where it exits. It exits where we know it exits, which is at that point right there, okay? Not a problem. This blue line has been drawn with a gradient of negative 1.75 approximately, and that represents this profit equation. And when we slide it through, and lo and behold, this is what happens. It's parallel to this green constraint. All right? It's parallel, and so it hits in more than one place. These points of intersection are my optimum solution points. We know that. This point here and this point here hold my optimum solutions because they're points of intersection. The thing is that this line here, when we draw the gradient, it hits both those lines at the same time because it's parallel. Now, if you test it, you don't believe me, I mean, you can see it physically, but it's going to be harder for you to animate this and show this physically by drawing a picture, a line, because it may be difficult to draw a line. But if you look at the gradient for this constraint here, if you work it out, you're going to get obviously the same gradient as you got with this. Same gradients. All right? And that's why you're getting, this is where the explanation comes in, that's why you're getting two different combinations, these combinations here, that are giving you the same maximum profit. Because this line is parallel. So what do we have again? Old constraint, X is through this 9.333, 18.6666. And the new constraint, which has the exact same gradient as this green constraint, the new maximum profit equation, the 49x plus 28y, being parallel to that. And so that's the conversation that you have. That's how you explain the two different combinations giving you the same maximum profit. So this is basically what you're going to have to show to get your excellence. You have to show the work that you've done, which is pretty basic. Just giving you the points and showing, substituting them in and getting your table. But then you're going to have this conversation about why. Obviously, the actual answer is the combination of 4 and 28, because we can't use 9.33 and 18.666. We've already established that. So this combination giving me a maximum profit of 980 is my answer. The problem is you have to discuss why you're getting two different, and so you have to talk about the fact that you're getting two answers or two combinations that give you the same profit equation because the 49x plus 28y is parallel to the other constraint, the constraint of 7x plus 4y less than 140. And so you have to have that conversation. If you don't use this word and don't explain the situation that's happening in the table about parallel lines and so on, then you won't get your excellence. And that's why being able to show the gradient, being able to determine the gradients, how they affect the feasible region and how they combine with the other constraints, you have to be able to talk about that to get an excellence on this linear programming question.